Logic is the study of valid arguments. Now, an argument has a structure. So for example, I say, if I go all in on black and the spinner lands on black, then I win $1 gazillion. There are 3 sentences in this argument. The first 2 are called premises, and the last one is called the conclusion. Premises are statements which come before the conclusion, basically. The conclusion is usually signaled by the word therefore, or then, or something like that, right? Now there are 2 measurements for a valid argument. The first one is consistency. Consistency means that every sentence in the argument, so here's 3 sentences, has to be able to be true at the same time. So there can be no contradictions. So for example, if I had a sentence that said like, it is true that the water is cold, and then later I have a sentence that says it is not true that the water is cold, then it's contradictory, right? And so as long as there's no contradictions in the argument, it meets the requirement of consistency. Validity means that assuming all of the premises are true, the conclusion has to be true. For example, if I said, I go on black, the spinner lands on black, and therefore I win $1 gazillion. If both of these are true, then the conclusion has to be true, right? Can you imagine a universe where I go all in on black and the spinner lands on black and I don't win? No, that's not possible, right? So assuming that these are true, this has to be true. But the key word here is assuming, right? So for example, if I had an argument that said like, I'm a bird, all birds have wings, and therefore I have wings, right? We know that this is not true in our world, right? But we have to imagine an argument as its own little reality. And so, assuming that I am a bird, there's a possible world in which I could be a bird, and where all birds have wings, then in that world, the conclusion has to be true that I am a bird, right? And so, these are the 2 requirements for a valid argument. Now this lesson will be split into 3 parts. The first part will be talking about clauses. And in talking about clauses, we're going to look at truth tables and simplifying words into symbols, right? The second part is going to be sentences. In the sentence part, we're going to look at how to translate sentences into symbols and then seeing how to calculate consistency, especially in sentences that get a lot more difficult. We're going to need to use a strategy called the Tableaux Method to calculate consistency. And then the final part is looking at entire arguments. So a set of sentences plus a conclusion, right? And then we're going to calculate whether or not an argument is valid through a method called extended truth tables, right? So, part 1, clauses. So when we look at clauses, we need to know what a declarative sentence is. A declarative sentence is any sentence that fits into this. Is it true that X? Okay, any sentence that can be substituted into X is a declarative sentence. So for example, fuck is not a declarative sentence because is it true that fuck is not a grammatical sentence, right? However, if I had a sentence that was like, is it true that I exist? Then the sentence I exist is a declarative sentence, right? Logic only ever deals with these declarative sentences. And the importance is that they have a truth value, right? Is it true that? It can be true or false, right? There's only 2 combinations, right? It's either true or false. And then when we deal with clauses, what we need to do is break a sentence down into its smallest constituent parts. A constituent part is what something's made out of, right? So what we want to do is break a sentence down into the smallest parts which still meets the requirement of being a declarative sentence. So for example, let's say the sentence, hydrogen is present, and oxygen is present. This sentence has 2 constituent parts, right? The first part is the sentence, hydrogen is present, right? And then the second part is, oxygen is present. These 2 can both fit into this structure here. Is it true that hydrogen is present? Is it true that oxygen is present? And so they qualify as declarative sentences, right? And so we can actually treat these as two separate sentences with the relationship between them being the word and, right? So now let's call H2 as present. Let's call this sentence A. And then let's call O2 as present. Let's call this B, right? So in symbols, this would simplify down to this here, A and B. This symbol is the symbol for and, right? So when is this sentence true, right? The sentence A and B, hydrogen is present and oxygen is present, is only true if both hydrogen is present and oxygen is present, right? If both sentence A is true and sentence B is true, right? If it's only true that hydrogen is present and it's false that oxygen is present, then the sentence hydrogen is present and oxygen is present would be false, right? If it's the other way around and it's hydrogen is not present and oxygen is present, then the sentence hydrogen is present and oxygen is present is also false, right? If neither is present, the sentence is also false, right? This here is the truth table for the sentence A and B. Any sentence that can be simplified into the structure A and B will give this set of results, right? This symbol and is called a truth functor. It's like a mathematical function. You give it a set of inputs, it gives you a set of outputs, right? It gives you a set of outputs of truth values. And this is the input, this is the output. Okay. Now let's say I have a sentence that's like, you can either subscribe to ACG Ethics Club or go for a run, right? Now this is very similar to this one in that it has two constituent parts, right? It's also A something B, but in this one, it's A or B. This is the truth functor or, right? You can either do this or you can do this, right? And in this case, the sentence A or B is true if both A and B are true, and it's true if only one of them are true. So if only A is true and B is false, the sentence you can either do this or that is still true, right? The only way in which the sentence A or B is false is if both A and B are false. Now these truth functors are defined by the set of results that it gives, right? The truth functor or will always give this set of outcomes for any sentence that is A or B, right? This is very important. We'll see it later. Now the third truth functor is this one here. This is called the negating truth functor. It basically translates to, it is not true that A. This one is relatively simple. It's just the inverse of A. So for example, if A is true, then not A has to be false, right? If A is false, then not A has to be true. That's just how it is, right? Now the last one, more important one, is this one here. A, therefore, B, right? So for example, if I had the sentence, if my gas tank breaks down, then I have to repair my car, right? My gas tank broke down would be A, and I have to repair my car would be B, right? And so if it's true that my gas tank broke down and I have to repair my car, then the sentence is obviously true because, my gas tank broke down and therefore I have to repair my car, right? But if it's not true that my gas tank broke down, but it is true that I have to repair my car, is the sentence A, therefore B, still true? Is the sentence, if my gas tank broke down, then I have to repair my car, is it still true? Yes, it's still true. Because just because it's not true that your gas tank broke down doesn't mean that in the case where it does break down, you don't have to repair your car, right? Now the only case in which A, therefore B is false is actually if A is true and B is false. Because if your gas tank broke down and you don't have to repair your car, then the sentence, if my gas tank breaks down, then I have to repair my car, doesn't make sense, right? And therefore, it's only if the, I guess, cause is false, and if the cause is true and the outcome is false, then this therefore relationship wouldn't make sense, right? If both of them are false, for example, if my gas tank didn't break down, I don't have to repair my car, then the sentence, if my gas tank did break down, then I have to repair my car, is still true, right? Because we're just saying that in the case that it does break down, it will hold to be true. Okay. Sorry, I just got kicked out of class. So now remember I said that these truth functors are defined by the set of outcomes that it gives, right? Now this is a very interesting property because it gives rise to this idea of logical equivalence. So if we look at this one in particular, A therefore B is actually the same thing as not A or B. A therefore B is the same sentence as not A or B. Why is this? It's because, look, if I had A and B and the sentence not A or B, and I have the same set of inputs, T, T, F, T, T, F, F, what would be the set of outputs for not A or B? Let's try to work this out, right? So if A is true, then not A is false. If B is true, then B is true. If not A is false and B is true, then the sentence not A or B is true, because only one of them has to be true for the truth functor or, right? If A is false and B is true, then not A is true and B is true, and not A or B is true, because both not A and B are true, right? If A is true and B is false, then the not A would be false and B would be false. This would be the only case in which the sentence not A or B is also false, right? Because both not A and B are false. And if not A is false and A is true and B is false, then the sentence not A or B would still be true because only one of them needs to be true, right? Look at this. This is the set of outputs we care about, and it's the exact same as this one, right? So we can actually translate A therefore B into not A or B. This becomes very, very important later on. I'm going to keep it there, right? This is logically equivalent. Now that we finished looking at clauses, here's how we translate every clause into symbols. Now we can look at translating an actual sentence into symbols, right? So for example, if we had the sentence, if the sun disappeared, then the oceans would freeze and we would all die. This has three constituent sentences. The first one is that the sun disappears. The sun disappears would be A. The second constituent sentence is the ocean would freeze. This is B. And the last one is we will die, C. Right? How do we translate this into symbols? There's actually a truth functor here that affects more things than the other. And that one is this word here, then. So this actually translates, so look, it says if the sun disappears tomorrow, then both of these would happen, right? So we actually need to put these with brackets around them. So it actually translates to A, therefore, bracket, B, and C, right? And so this truth functor has a bigger scope. It means that it affects more variables than this truth functor here, right? This one's inside brackets. This one's outside the brackets, right? And so this is the main truth functor, right? It's the one outside all the brackets. Now let's take a look at a set of sentences and see whether all the sentences in that set are consistent. Remember, consistency means that all of the sentences can be true at the same time, or that they're not contradictory. For example, if I have A and not A, then that's contradictory, right? Usually it's very easy to see if a sentence is consistent. But when you have cases like this, let me read this out to you. Let's see if you can work this out just by reading it, right? If lithium is present and copper is not, a green solution appears. That's sentence 1. Either copper or magnesium is missing. That's sentence 2. lithium is present, but only a blue color appears. That's sentence 3. Is this consistent? Can you work it out just by listening to it? It would be very difficult. Okay, and so in order to see if this is consistent, we have to use something called the Tableaux method. Here's how you do it, right? First of all, let me write this out. Okay. First, what we want to do is translate this set of sentences into symbols, right? How do we translate the first one? If lithium is present and copper is not, then a Greek solution appears. So these two sentences, lithium is present, A, copper is not, B, need to come together, right? So A and B, therefore a green color appears, C. So it actually translates to A and B within brackets, therefore C. Right? If lithium is present and copper is not, would translate to A and not B, therefore C. Right? So the first sentence is A and not B, therefore C. Right? Now the second sentence is either copper or magnesium is missing, meaning either not B or not D. Right? Like copper is missing would be not B, magnesium is missing would be not D. Right? The third one is lithium is present, but only a blue color appears. Right? Lithium is present is A, but only a blue color appears. A blue color appears means that a green color did not appear. Right? And so this would mean that A and not C. The third sentence would translate to A and not C. We usually just put brackets around every sentence. How do we test this system? We take any sentence from this set, and then we draw something called a tableau. Right? Here's how it works. Let's say I take this one here, A and not C. Right? In order for A and not C to be true, both A and not C has to be true, right? And so we draw a line down here and it says A and not C, right? Next, let's take, for example, this sentence here, not B or not D, right? Not B or not D has two possible ways in which it can be true. Either not B is true or not D is true, right? This is fair enough. Now we have two cases. It's branching off into two cases. And then lastly, we have this sentence here, which is more complicated. A and not B, therefore C. How do we deal with this one here? This therefore. Here's where logical equivalence comes in. Because if you remember, A and not B is actually equivalent to not A or B, right? Which means that this, in order for this sentence to be true, either it's not true that A and not B. Let's say that we treat A and not B as just like its own thing, like D, right? D therefore C, right? If it's D therefore C, then it's equivalent to not D or C, right? And so we get this not A or B or C, right? It's either this is, it's either not true that A and not B is true, or it's true that C is true, right? Now, here's where we can find out if it's consistent, right? Here's C, and then further up we have not C. Now this is contradictory, right? And so we draw a line under the C, and then we close off this possibility of the table, right? If all the possibilities in this table are closed off, then it's not consistent. And so let's work out every other possibility, right? Now we have this one. It's not true that A and not B is true. How does this work, right? In this case, there are also two solutions. Either it's not true that A is true, or B is true. If it's not true that A is true, oh look here, not A, A. Cross it out. Not B, not B. This is valid. Oh wait, no. Not B and B, this is also contradictory, right? Because this contradicts this one. So we cross it out. Now, this one here, how did I get to this conclusion? Well, you don't have to memorize it, really. There's a whole table that you can find online, and I'll link it below. Now let's move on to the other side, right? Not D. This actually follows the same thing as over here. We just draw either it's not true that A and not B, or C closes off. The only difference being that now, when we come down to B, not A is still closed off because A and A are contradictory. But the only difference is that now when we come down to B, B doesn't contradict this one because this is on the other side, right? Now we have a not D instead of not B. And so B over here, we have A, not C, not D, B, right? None of these are contradictory. And so we have one possibility where it could be true that all of the sentences are true altogether. And so this sentence, if lithium is present and copper is not, then a green solution appears. Either copper or magnesium is missing, lithium is present but only a blue crystal appears, is actually consistent because not all of the possibilities are closed off. Now lastly, let's look at an entire argument. The only difference between the sentence we just looked at and a proper argument is that a proper argument needs a conclusion. And so let's say that we have this argument here. Okay, let's say that we have this argument right here. This is a sentence, Q therefore P. This is sentence 1. Q therefore not P is sentence 2. And then this symbol here is what makes the difference between a set of sentences and an argument. This is called a semantic turnstile. It basically entails the conclusion. It signals that whatever comes after this is the conclusion. And so not Q will be the conclusion, right? How do we work out whether or not this is true, this is valid, right? Let's go back to the definition of valid. Assuming all the premises are true, these are the premises, this is the conclusion must be true. So if, for example, this sentence is true and this sentence is true, then there will be no way that this conclusion is false, right? If this is what happens, the sentence is not valid. If it's like this, where in all cases where the premises are true, the conclusion is true, then it's valid. Okay, so how do we test this? We use something called a truth table. It's very similar to what we did here, but it's going to take a little bit longer. Right? The only variables we have right now are P and Q. Right? And so there's only 4 possibilities. True, true, false, true, true, false, false, false. There's only 4 possibilities. Now, what we need to do is go and fill out this entire table. And so we start from the simplest. Thing. For example, if Q is true, then Q is true. Q is true. Not Q is false. If P is true, then P is true. Not P is false. Okay. So if Q is true and P is true, then the sentence Q therefore P has to be true as well. If the sentence if Q is true and not P is false, then the sentence Q therefore not P, let's see it here, right? If it's true, false, then A therefore B is false, right? And so this is false. And so we have this sentence is false. Wait, no, this sentence is true, this sentence is false, and the conclusion is false, right? We don't really care. We only care about the cases in which this sentence is true, this sentence is true, and this is true, right? If in all cases where we only care about the cases in which both of the premises are true, right? If there's a case where both premises are true and the conclusion is false, then it's not valid. Okay, so let's keep going. And then, wow, look at this one. Now we have the first case where both premises are true, right? If both premises are true, the conclusion is true. This is all good. But if we have another case in which both of these are true, then this also has to be true, right? So we need to keep going because it's in all cases where the premises are true, the conclusion has to be true. This is only one case. This is one case. This is one case. One possibility. So we need to keep going. Down here, we have another case where both premises are true and the conclusion is true. And so there's two cases in which both premises are true. And in both cases, the conclusion is also true. And so in all cases where the premises are true, the conclusion is also true. And so this sentence, this argument here is a valid argument. Valid. Okay.